Okay, well, you might not know anything about catalytic converters yet, but you probably do know that they contain something expensive because people keep stealing them from cars. So catalytic converters contain typically platinum, very expensive rare metal. Okay, here, let's talk briefly about how they work. All right, here's a diagram of a catalytic converter. Exhaust from the engine comes in. The exhaust contains some things that we don't want. Unburned fuel, or only partially burned fuel, in the form of carbon monoxide, a poisonous gas, and nitrous oxide, which itself is bad, but also is a principal component of smog, okay? These go into the catalytic converter. In the catalytic converter, the presence of catalysts, typically platinum, and the high temperature, allow the oxidation of these fuels, of these unburnt hydrocarbons, to happen very rapidly. And what comes out of that catalytic converter then are much more benign substances like water and nitrogen and carbon dioxide, okay? May be bad for global warming, but at least it doesn't cause smog, okay? The catalyst in this case is, as always, it's a substance that makes the reaction go much faster, but itself isn't consumed in the reaction, okay? In this case, the catalyst consists of a kind of a honeycomb, a sort of mechanical scaffold that holds small particles of rare earth metal, typically platinum, but also palladium or rhodium could be used. Each of those is very expensive as well. Okay, that's a catalytic converter. And my question for us is, the particles of platinum that we put in here, how big should they be? Should they be big, lots of platinum? That's got to be better, right? Or should they be small? Or should they be nanoscale? Okay, hang on. Okay, so catalytic converters use platinum as a catalyst. To burn up partially burned hydrocarbons to make the exhaust of cars more benign, okay? And the issue, of course, is that platinum is really expensive. At the moment, it costs about $630 for 1 cubic centimeter of platinum, okay? Not as expensive as gold, but pretty expensive, okay? And another issue is that only atoms on the surface of the platinum particles can catalyze reactions, because obviously those are the only atoms that are exposed to the gas. Okay? So if we're making a catalytic converter and trying to decide how big the pieces of platinum should be, then we probably want to worry about this. We want to worry about the effect we're going to get divided by the cost that we're going to have to pay for all the platinum. Okay? Now, the effect, of course, is proportional to the number of atoms on the surface, which is proportional to the surface area. The cost is proportional to the volume, or really the mass, and that's proportional to the volume. So the all-important ratio, bang for your buck, effect for cost, is proportional to the surface area to volume ratio, okay? Surface to volume ratio. And you can see that that's then itself proportional to, well, the surface area is going to be proportional to the characteristic dimension of our particles squared. Whereas the volume is going to be proportional to their characteristic dimension Q. Notice I haven't told you what shape the particles are. They might be little spheres, they might be little cubes. It doesn't really matter. Okay, it matters as a detail, but but the overall the most important thing is that area goes like characteristic dimension squared, whereas volume goes like characteristic dimension cubed. So it goes like 1 over the characteristic dimension. And so clearly, we'd like to make the platinum particles as small as possible. Okay? If we can make them smaller and smaller, it's better and better. Just to illustrate, let's make a little table of characteristic dimension. Oh, let me be a little more clear. Let's do the following. Imagine we have 1 cubic centimeter of carbon to burn, well, to use to make up our catalytic converter. And but we can divide it up however we want. So we can have our initial volume, 1 cubic centimeter, and we could have it as 1 piece, or we could have it as 10 smaller pieces, or 100, or 1,000. We can make the pieces as small as we like, but the total volume is always going to be 1 cubic centimeter. Okay? So our characteristic dimension of our particle is 1 centimeter. Then we're only going to be able to have 1 cube. And its surface area will be, of course, 6 cubic centimeters. The cube has 6 faces. And so since it costs about $600 for this cubic centimeter, the cost in dollars per square centimeter of area, okay, oops, I wrote cube, but I meant squared, will be $100. Each square centimeter of platinum will cost $100. Let's suppose that instead we make them not 1 centimeter, but 1/10 of a millimeter, okay? Well, now we can have a lot more cubes, okay? Give me 1 second. Okay. Now, what's the surface area of 1 cubic of our original volume of platinum, 1 cubic centimeter before we cut it up into cubes, but now divided into cubes that are each only 1/100 of a centimeter across? Well, it's not hard to figure this out. One way would be to figure out what the number of cubes we would have would be, and then figure out what the area of each one is, and then multiply those two numbers to find the result, okay? The number of cubes would be the following. We just take the initial volume and divide it by the volume per cube. So the initial volume is 1 cubic centimeter. And when we divide it, and the volume of each cube would be 1/100 of a centimeter by 1/100 of a centimeter by 1/100 of a centimeter, or 1/1,000,000th of a cubic centimeter. We'd have 1,000,000 such cubes, okay? Now we have to multiply that by the area of each cube. The area of each cube would be 6 times the area of each face, and the area of each face would be 10 to the minus 4 centimeters. So we have 10 to the minus 4 times 10 to the plus 6, or 600 cubic centimeters. I'm sorry, 600 square centimeters. Okay? So the cost per centimeter squared of area now is only $1, 100 times better. Isn't that great? Okay. By the way, we could have done that problem we just did in another way that would make it easier. we know that the surface to volume ratio goes like 1 over d. And we know that the volume is being held constant. The total volume is being held constant. So if we make d 100 times smaller, then it's pretty clear that the total area has to go up by a factor of 100 because the surface to volume ratio goes like 1 over d. Okay, in any event, let's go on. Suppose we made the cubes only 1 micron on a side, okay? A millionth of a meter, or 10 to the minus 4 centimeters. Then we would have 6 times 10 to the 4th cubic square centimeters of area. So 60,000 cubic centimeters. Now, each cubic centimeter would only cost 1 cent. Finally, we could imagine make them only 10 nanometers. Now, our cube is very small. It's only a few tens of atoms across. But still, it's possible to make platinum into such small particles. Okay? Well, in this case, because we've reduced the size by another factor of 100, the area has to go up by another factor of 100. So now it's only 100th of a cent per square centimeter, okay? And what's more, our original volume of 1 cubic centimeter has now been spread out over an area that's 24 by 24 meters, okay? This huge area now covered with platinum, only in a very thin layer, but it's only the surface. It's only the atoms on the surface that make any difference. Okay, let's stop this example here.